Calculating the eigenvalues of a finite matrix produces a predictable set of points, but in infinite dimensional spaces, operators can produce a continuous spread of spectral values that is difficult to analyze. Compact linear operators serve as the mathematical bridge, forcing these infinite systems to follow the more structured rules of finite matrices. This contrast reveals the environmental shift. A finite matrix yields a point spectrum, while an infinite dimensional operator produces a continuous spread. But a compact operator replaces this spread with distinct points, sequencing downward to accumulate exactly at zero. Three tools are required to prove this behavior: the eigenvalue equation, the resolvent operator used to test for bounded inverses, and the formal partition of the spectrum into point, continuous, and residual parts. This accumulation at zero is the geometric constraint of the Rees-Schauder theory. Understanding how zero limits the operator provides the structure necessary to solve advanced problems in functional analysis. Theorem 8.3-3 states that for any compact operator, the eigenspace corresponding to a non-zero eigenvalue is finite dimensional. We begin the proof by defining M as the closed unit ball in the null space and selecting a bounded sequence xn within it. Because the operator T is compact, the mapped sequence Txn must possess a convergent subsequence. By substituting the eigenvalue equation, we replace Txn with lambda xn. We then divide by lambda to isolate our sequence, proving that xn itself converges. Since the unit ball is compact, the space must be finite dimensional. Examine that final algebraic step and consider what happens to the logic if lambda is equal to 0. If lambda is 0, division is impossible. This mechanical failure prevents the unit ball from being compact, explaining why infinite dimensional eigenspaces can only exist at the zero coordinate. This leads to Theorem 8.3-1, which limits the number of eigenvalues a compact operator can have, and requires any infinite sequence of them to accumulate at zero. Using Rees' lemma, we build expanding subspaces, from a line to a plane to a volume. Each new dimension adds a vector that maintains a minimum distance of 1/2 from the previous geometry. If we track these vectors through the operator, the distance between them is governed by the size of the eigenvalues. If the eigenvalues remained above a positive constant, the vectors would stay separated, making it impossible to form the convergent subsequence that compactness requires. To satisfy the definition of a compact operator, the distance between mapped vectors must shrink. This forces any infinite sequence of eigenvalues to accumulate at zero. We can analyze the operator further by raising T lambda to ascending powers, mapping the behavior of its null spaces and ranges. Ascending null spaces expand until they stabilize at index r. Simultaneously, descending ranges shrink until they stabilize at index q. Theorem 8.4-3 shows these stabilization indices are identical. This identity creates a direct sum, partitioning the entire space into two separate non-overlapping components. This split proves Theorem 8.4-4. If a non-zero value is not an eigenvalue, its null space is 0. In this direct sum, if the null space is 0, the range must encompass the entire space. Because the operator is now both injective and surjective, it possesses a bounded inverse. This proves that continuous or residual spectra cannot exist for non-zero values. Having established the rules for non-zero values, we now test the zero coordinate itself to locate the continuous and residual spectra. Consider a right shift variant on sequence space L2. Its eigenvalues form a sequence 1, 1/2, 1/3, trending towards 0. Testing 0 proves the operator is injective, meaning 0 isn't an eigenvalue. But since the range is dense yet not closed, 0 falls into the continuous spectrum. In a compact operator, the infinite dimensional anomalies, such as the continuous spectrum, are restricted to the zero coordinate. This summary outlines the core distinctions for competitive exams. Unlike finite matrices, compact operators have countable eigenvalues, with 0 as their only accumulation point. For any non-zero value, the spectral value must be an eigenvalue with a finite dimensional eigenspace. Mastering these constraints allows you to apply the predictable logic of finite systems to complex infinite dimensional problems, forming the foundation of modern functional analysis.